Hello, welcome to your module 4. Okay, so we are now on the shear and moment of beams. So in this slide, we will be discussing your unit 1, which is about the shear and moment equations and then the shear and moment diagrams. Okay, so we are going to discuss how to establish equations of the shear and moment in the beams that we are considering, and then of course we are going to relate that with the drawing, and these are the diagrams. So for this unit, we will be having these learning outcomes. So first is for us to define what is shearing force and then your bending moment, and then of course to draw your shear and moment diagrams using our shear and moment equation that we are going to establish. So this is the introduction. So before we will proceed to the shear and moment, we will first try to recall some of the important terms here, especially about the beams, which you discuss in your statics of rigid bodies. Okay, so beam. So a beam is a member which resists a transverse loading and forces by bending elastically. Okay, so your beams will react by bending. Okay, if we say elastically, we are just considering here the elastic stage. Okay, as we discussed in your what we call this one in your previous module 3 about the yielding stage, the elastic stage, and the plastic stage. Okay, so for the analysis in this shear and moment, we will be considering the elastic, okay, the elastic stage. So a bar subject to forces or couples that lie on a plane containing the longitudinal axis of a bar is called a beam. Okay, the force are understood to act perpendicular to the longitudinal axis. So actually there are a lot of scenarios if we are talking about beams, and there are these simple discussions, and this is where we are going to focus ourselves on the foundation of beam, or we will just try to discuss these simple scenarios of beam, since actually there are advanced topics of beams, and that will be discussed on the advanced subjects. Okay, so for the limitation of this discussion, we will try to limit ourselves. Okay, on the first, we will consider all forces acting on the beam lie on the same plane. Okay, so they will act on a single plane. This longitudinal plane passes through the centroids of all the cross sections of the beam. Okay, so we will consider all the forces that are passing through the centroid of the beam, so that we will just be analyzing the beam under pure bending, because if that will now be acting somewhere not on the centroid, then that will create what we call as torsion. Okay, and we discuss about that. So second limitation is that the elastic limit of the beam material is not exceeded. That's why I mentioned a while ago we will just be considering on the elastic stage, because once we will surpass that elastic stage, the behavior of the cross section will be different. Okay, so we will try to limit ourselves on the elastic stage. And then third is the cross section of the beam is uniform in size and shape for the entire length. So we will try to consider a beam which is prismatic. If we say prismatic, the cross section all throughout the length are the same and the dimension. Okay, and then fourth is the beam is thick enough to prevent localized buckling or wrinkling. So we will try to consider again that the beam will withstand the bending without failing through buckling. Okay, so that will not buckle. So let's consider that that is thick enough. And then lastly, vibration, shock, and impact loading do not occur. So we will just consider the ordinary type of loadings, wherein that could be concentrated load, that could be distributed, triangular, and so on and so forth. But of course, without the what we call this one, vibration, shock, and other types of loading on the beams, which is actual type of loading. Okay, so they call on cantilever beams. If we say cantilever, that is on the other end. Okay, you can read about this on this description here, but I will just be discussing it shortly so that we will not be taking much of our time. Okay, so cantilever beam, we are just referring here to a beam which is fixed on the other end and that is free on the other end. So that will bend, of course, downwards as given by this type of loading. Okay, so cantilever beams. And then we have what we call as the simple beam, or that is a simply supported beam, wherein your supports on the both ends are simple supports. If we say simple supports, this could be a hinge or a ruler. Okay, So actually, why are we considering this? Okay, in this analysis, we will try first to limit ourselves on determinate. Okay, we already discussed what is determinate, wherein the reactions or the analysis of the entire system could be done by plainly statics of equilibrium. Okay, so we will try first to focus on the systems wherein we can just solve the reactions by means of the static equilibrium equations. So simple supports. So we have here simple supports on both ends, so there will be no moments. But in case there will be a fixed here, then just like in your cantilever, isn't it? What are the reactions expected here? Horizontal, of course, but there is none because there is no horizontal loading. So summate horizontal, there will be no horizontal reaction. You will expect here a vertical, of course, since we have here a vertical loadings. And of course, we will expect here a moment since that is a fixed support. Okay, so later on, that reaction of the moment and the vertical will be considered in establishing the diagram in the equation for the shear and moment. In here, in your supports, we do not have there a moment, of course, since we only have there a horizontal or vertical. But again, in here, summation of horizontal, we will not care about that since there is no horizontal loading. So we will only end up here with a vertical supports or reactions. So that will be included in our to establish the equations and the diagram. Okay, you can read about that again. So we have here your overhanging beams. Okay, if we say overhang, that is actually what they call this one, an extension, or just like a cantilever. The scenario is like a cantilever, but of course your other end is not a fixed, or I mean it is a fixed since that is continuous, but the scenario is that it is connected to another beam on another span. Okay, so that is an overhang. In here, in your cantilever, that is plainly attached on a fixed support. So that could be a column. So that is a cantilever. But for a overhang, okay, that could just be supported in a part of the length of a ruler support. So just like this. So these are just examples of your overhang. But what do we expect here? The reaction, since that are simple supports, then you will only have their vertical, and again there is no horizontal unless you will have horizontal forces. But in case, okay, if you want to cut the beam at this point where the ruler is supporting your beam, then actually you can expose a moment here, okay, an internal moment, and actually that will be the same as calculating the moment support in your cantilever. Okay, the same way of calculating that internal moment. So the reaction moment here is the same way of calculating in your overhang moment. If I will try to expose the internal moment, if I will try to cut within your ruler here. Okay, so those are just the simple type of beams that we will just be including in our discussion. Okay, so again, statically determinate beams, so that is what we will be considering. Okay, so that we will only be using the static equilibrium equations. So of course we have here your indeterminate, that will be on your next topics. Okay, so again, for example, here in your figure A, you have here a cantilever at the same time that is propped or that is supported by a simple support here. So counting the number of reactions, okay, that we need to solve, then that will be 4, and we only have 3 equations of equilibrium. So again, that is why we consider this indeterminate, because we cannot just use the plain equilibrium equations. And so with your second equation here, or second figure I mean, in your figure B, that is a fixed, so a total of 6 supports. Again, that is far more than the 3 equations of equilibrium. And in here, look at that, 3 simple supports. So actually 1, 2, 3. 3 vertical supports, 3 vertical support reaction unknowns. However, there will be 4th here, which is your horizontal. But even if that is 0, but that will actually also neglect the summation of horizontal forces, which will reduce our equilibrium into 2. Only summation of moment and summation of vertical, which is 2, and compare it to the unknown 3. We cannot do that by rule of algebra, of course. So this will be considered as, these are just some of the indeterminate, okay, situation of our beam, and then that will be of course on the other discussion, on the next discussions. Okay, so again, since you discussed already in your statics how to calculate the reactions, okay, of indeterminate beams, then I think we will proceed. Okay, I will not be discussing again how to calculate summating moment and so on and so forth, because we will try to have that once we will try to solve examples. So if we say internal forces and moments in beams, we are now trying to investigate the beam itself. Okay, so we will try to cut the beam, okay, the member, and then we will try to expose how much force that is holding, and then moments. Okay, we will try to find out the member forces and member moments, and that is what we call as the internal forces or internal moments. Okay, so in this problem, okay, I mean in this example, in this figure, look at this. We have here a beam which is loaded by 4 concentrated loads P1, P2, P3, and P4, and that is supported at A and the other end by simple supports. Okay, so there is of course a simple solution for you to solve the reaction, so that is using your equilibrium. So once you have that reaction, then we can now actually analyze the beam itself, the internal forces and the internal moments. Okay, so now for example, okay, I want to know, or I want to investigate how much force or how much moment the beam is experiencing within this part of the beam, okay, between the loading P2 and P3. Okay, let's say I will cut that one in this section, then I will expose. Okay, once I will cut that, then I will be exposing what we call as the internal forces and the internal moments. And this will be, okay, we will be expecting here a moment and then a vertical reaction, which is what we call actually as the shear. Okay, so again, this is just to expose. This is an internal forces and moments. Okay, so what is the reason why there is a moment and shear here? Actually, that will represent the effect, okay, of the other side of our beam. So if you want to analyze this beam by cutting at a section, then all you need to do is of course put back the effect of the other part that you remove. So let's say I want only to focus my analysis on this side, on this left side, then I can actually erase that right side, but I need to apply the effect of that on the beam that I am considering, on the side that I am considering. And the effect of this right side is actually your internal moment and then your internal forces or internal shear. Okay, so how do we solve this one? The same, just like of course, just like solving your reactions, all we need to do is apply your equilibrium equation, summation vertical, summation horizontal, and then summation moment. But as you can see, we do not have here horizontal, so we will not be having a horizontal internal force. Okay, so okay, you can read. I will not be reading your discussion here, since your module you are provided a copy, so you can read about that. But actually, what is stated here, I am discussing it verbally, okay, through the figure. So okay, for example, you want to calculate the moment. So this is an example of computation. You want to take a moment, you want to get the within a certain distance, let's say that is unknown x, so let's say that is a certain distance x. So of course I will cut that section D, let's say that is section D, and I want to know the internal moment and the internal forces. Then all I need to do is summate a moment at D, and then I will figure out your moment, internal moment at D. Okay, and then summate vertical. Then given that you already solved your reaction, then I will solve that remaining vertical internal force, or that is the shear, internal shear. And then same thing, if I want to analyze this other side, let's say I want to analyze somewhere between P3 and P4, all I need to do is cut that one and then expose. But of course that is different in your section D, because the distance, okay, that I am considering will be different. So that's it. And actually analyzing this beam, I need to know what will happen within this part AB, BC, within this part between P2, P3, P3 and P4, and then on the last part, because actually the situation of this beam within these different parts will be different, because of course we have here additional load. As we go on to the right, let's say I want to analyze from the very leftmost part to the last point on the right side, then as I go on to the right, there will be additional loading that I will consider. So the scenario in each of these division will be different. Okay, so that is actually what we are going to establish. Okay, we are going to represent the effect of this loading at a certain distance. Okay, we are going to represent that one into a single scenario, and that will actually be represented by what we call as the equation. So that once you have your equation, all you need to do is substitute. Okay, you want to know the internal moment and then internal shear at that certain distance from A, then all you need to do is input the value of x. So as you can see here, our equation, so for example, this is an example of moment equation, and that is derived at your section D, or that is derived within this part of the beam, okay, between P2 and P3. So that means that, let's say I want to know what will happen, or what is the internal forces and moment within somewhere here, okay, a little bit longer than D, that is still within your divisions between P2 and P3, then all I need to do is change the value of x that I will substitute. Then I will end up with another moment, because the moments all throughout the beam are different. Okay, the moments within the length of the beam are different at a certain distance, and so on with the shear that we are referring to. So okay, same thing as your V. In here we try to summate moment at D, so that we will end up with the internal moment. And then same thing will happen in finding your internal shear or your shear. Summate moment, I mean not moment, summate, you can do moment once you already established, but your M is in terms of equation. So that will be making your shear equation a little bit longer, or longer compared to what is supposed to be. Therefore, to neglect that one, or to avoid that one, then we will be doing the summation of forces vertical, for us not to include that moment here, which is in terms of equation. So what will I be doing? Summation forces vertical, I will end up here with a V, which is in terms of equation. Okay, in terms of equation. Okay, so those will be our equation, moment, and then shear equations. But actually that will be different. This is just an example in this scenario. Okay, we have a lot of scenarios because there will be different types of loading and so on and so forth, and then we have of course different types of reactions, and I mean supports, and then of course different lengths of beams. So this is just for example only. Okay, so now let's try to discuss what is bending moment. Okay, what is the relationship of this bending moment if I will consider this left side and right side. Okay, as you discussed in your equilibrium, if you are trying to analyze a certain system which is static, if we say static, not moving, it is not moving, then the equilibrium should be, or that's why we are using equilibrium, because if you are trying to summate moment and then forces, that should be equal to 0. So same thing, even if I will try to cut at that section D and then analyze this side, that should be satisfying the equilibrium. Same thing if I will consider the other side. Okay, that will still be in equilibrium. But the question there, what if I will consider the right and the left? Will that give me the same V and M at a certain section? Of course, yes, since you are considering a single beam. Okay, in the analysis, in this example, I only consider the left side. But if you want, you can consider the right side. Don't worry, we will be having an example like that. Okay, I will be showing you the solution using the left side and right side, and then that will end up still with the same values. Okay, so if I will try, for example here, I want to consider this right side instead of the left side. If I will try to cut that one and consider this, the moment here, if I will try to summate, even if you are dealing with different forces here, that should be the same with the moment M on your left side. Same thing with the shear. But of course, since you are considering the different sides the same value but opposite directions. Okay, of course you know that one. For example, if I want to cut that one, you solve your B and M and then transfer that one on the other side. Isn't it that is discussed in your statics? You need to reverse. You need to reverse the direction, since that will serve as a reaction. Okay. So the same thing will be. Okay, so that is what I've discussed verbally. So you can read again about your discussions here. And then we will be following a certain sign convention, so that we will not be what to call this one. We will not be confusing ourselves. We will try to follow a certain sign convention. If you want, you can follow an opposite sign convention on what we will be doing, but you need, of course, to indicate that one. Okay. So for this discussion, we will try to consider a sign convention wherein if the beam is deformed this way, okay, it will be opening upwards since due to the loading, then the moment will be positive. If the moment will try to bend your beam and that will curve upward, that is a positive bending moment. Okay, so that is how we will be knowing if your bending is a positive or negative. And then how about if we are talking about shear? Okay, if we will try to consider shear, the positive shear will be the shear that will make your left side what to call this one, deflected upwards relative to your right side. Okay, or the other way, your shear that will make your right side deflect downwards relative to your left side will be the positive shear. Okay, and if that is the other way, then that will be the negative shear. The same thing with your bending. If that will try to bend the beam and that will concave downward, then that is a negative moment or negative bending moment. Okay, so we will now be having your shear and moment equations and then together with the diagram. Okay, so usually it is convenient to introduce a coordinate system along the beam with the origin at the end of the beam. Okay, at one end of the beam. It will be desirable to know the shearing force and bending moment at all sections along the beam, and for those purpose, two equations are written, one satisfying the shear force as a function of distance, say x, from one end of the beam, and the other giving the bending moment as a function of x. So going back to the figure, most of the time we will try to establish our equation based on a single point, which is on the leftmost or the rightmost. But since again most of the time we are doing it from left going to right, so we are establishing it from the very first point. Okay, from the extreme point on the leftmost side. So once I will establish an equation, which is I will consider the distance x from that leftmost point, then that is good for that scenario. But if you want to consider the distance, if you want to input a distance, which is a distance x, which is measured on this rightmost side, then you need to establish the shear and moment equation based on the distance x, which is coming from the rightmost side. Okay, so again, that is how you will do it. So for you to do that, then you need to consider the right side of the diagram. Okay, so let's try to be clear with that. So again, if you consider the left side, and of course, since of course we are going to establish a distance x there, that will be reckoned from the leftmost side, then that is true. Okay, that is only true if we are going to substitute a distance from the leftmost side. Okay, we cannot apply if the distance that we are substituting is coming from another point. Okay, your equation that you establish is based on a point, then that should be the scenario where you are going to substitute the value of x. Okay, so the plots of the equation V and M are known as shearing force and bending moment diagram. So if we are going to plot, since of course you know your equation, you can plot that one. If your equation is in terms of x and y, then you can plot that one in x and y axis. And then the plot of that is what we call as the diagram, shear and moment diagram. Of course, if you are plotting the shear equation, then that is a shear diagram. If you are plotting the moment equation, then that is a moment diagram. Okay. In these plots, the abscissa or the horizontal indicate the position of the section along the beam, or that is the distance x that we are referring to. And the ordinate will, or the vertical will represent, it's either the shear or the moment. It depends on which one you are drawing. If you are drawing the shear, then your vertical will represent the shear. If you are drawing the moment, then the vertical or the ordinate will represent your moment value at a certain distance. Okay. So thus this diagram represents graphically the variations of shearing force and bending moment at any section along the length of the bar. From these plots, it is quite easy to determine the maximum value of each of these quantities. So what is the purpose for us to be writing this equation and then for us to be drawing the diagram is, of course, for us to outline, okay, outline the scenario of a shear and moment experience within the entire length of the beam. So for example, you already established an equation and you want to know a certain shear or a certain moment at a certain cross section, then all you need to do is input the distance, okay, since your equation is in terms of x, which is a distance within the beam. Okay, same thing with your diagram. Once you already drawn your diagram, all you need to do is plot. Okay, once you already plot that one and you want to get a certain value of moment or shear, then all you need to do is use the graph to find out what is the value of that moment or shear within this given distance. So that is the advantage of this shear and moment diagram. So this is actually a very much or very important topic as a foundation if you will now proceed to your designs of beams, of course, and then the same thing with other members. Okay, so we will try to have this example. Okay, write the shear and moment equations of each segment of the beam shown. So we have here this scenario of the beam. Consider both the left and right side. So let's try to consider. Okay, I will show you how to do it using the left side and then the right side. That should be the same, giving you the same value. Identify the value of shear and moment at each of the chains of load points. So actually, as I've said, the scenario within this division of this, let's say that is segment AB, is different from BC and CD since we have different loading and different distances. Okay, so first is for us to establish, for us to, of course, later on you will cut that one, summate moment and then forces. You need to know the values of your reaction. Okay, so first is for us to solve the reaction. So the very first step is to solve the reaction. So it's up to you. Okay, so in my solution here I presented, I will summate moment at A, so that will cancel the reaction at A. I will only expose the reaction at D, then I can solve for that. So, okay, 15, that is a distributed, again, that is a distributed load, so multiply it by 2, so that you will make it as a concentrated, so that we can take the moment of that. Okay, so the distributed, transform that one into a concentrated, which will apply on the, or which will be concentrated on the middle of the UDL, if that is a uniform distributed load. Okay, so 15 times 2 is 30. That will be applying on the middle. So if that is 2 meters, then that will apply within the 1 meter from B or from C. And then take a moment of that. So okay, let's say summation moment at A and then clockwise is positive, so that will be my assumption here. 15 times 2, that is the concentrated force, and the moment arm to your A, since I am summating moment at A, is 1 plus 0.5, so that is 1.5, or 2 divided by 2, that is half of that, so that is 1, so 1.5. And then we have another force here, which is actually the unknown reaction. Let's say that is dV. It will be a counterclockwise moment, so that will be a negative, and then moment arm is 2 plus 2 plus 0.5 is 4.5. Algebra, simple algebra, equate that one to 0. Since that is equilibrium, we will have dV, which is 10. And then if I want to solve that reaction at A, I can do summation moment at D, and same thing, same process, summation moment, let's say clockwise positive, and so on and so forth. Solving for AB will be 20, or actually you can use the summation vertical, or you can use that as way of checking. Okay, so that is the good thing in your equilibrium. You can use the other equation to check for the other. So let's say I want to check summation of forces vertical. So that is 10, that is 20, that should be, that is going up, that should be equal to all the forces going down, which is 15 times the length, which is 2, that will be a concentrator of 30. So 20 plus 10 equals 30. Yes, so we have a correct reaction. And then now, this is now how we will start to write the equations. So again, as I've said, the equation within your segment AB is different from BC and CD due to the different types of loading. Okay, so let's try first to establish the equations in your first segment AB. So if I will try to cut within the length AB, okay, I will try to expose this internal moment and internal shear. This will be the left side, that will be the right side. So again, for this example, I will be showing you the two possibilities, considering the left side and the right side, and I will show you that will be the same. But later on, as we go on the other examples and then the next discussions, we will just be focusing on one. Okay, we will just be focusing on one so that we will not confuse ourselves. So if that is the case, then okay, I will try to assume the directions of my shear to be a positive. Okay, and again, what is our sign convention? A moment that will bend your beam to concave upward, that is a positive moment, and then a shear that will try to deflect your left side going up relative to the right side, then that is a positive shear. Okay, so for my assumption here, the direction for that to bend concave upward, that should be a moment like this, which is a counterclockwise. On the other side, the positive direction here is clockwise for that to concave upwards, for your beam to bend upwards. Okay, concave upwards. Or actually, once you assume a direction here, all you need to do is reverse the direction, since we are transferring the force on the other side. So again, that is the rule of transformation of your forces. Okay, so first I will assume here. So again, for that to be bending your beam upwards, that should be a counterclockwise moment. And then for us to have the right side deflected downwards, okay, that is again our sign convention. Your right side should be lower than your right side, or if you are on the right side, your left side should be, if that's a negative, that is the other way. Your left side will be lower than the right side. So for us to have a positive shear, then we need to have a going down shear for that right side to be lower. Okay, so that will be my sign convention. So if this is what I will be considering, the left side, then this will be my directions. That is just preliminary. Actually, you can consider different direction, any direction, but for us of course, not to be confused, we will try to follow the sign convention positive. Okay, but later on you will solve this MA and MAB and VAB, and you will end up with a negative. That only means that your assumed direction is the opposite. The correct one is the opposite. So all you need to do is reverse. Okay, so considering your AB, so I want to say the X will be referred from the leftmost side A. So whatever distance, okay, whatever section within your AB, that is a distance X. Okay, let's say that is a distance X, since we do not know that one. Okay, so your value of X will be from 0 to 0.5. Why? Because the farthest is B, which is 0.5 from A. So your values of X that I will input with my equation later on will only be from 0 to 0.5. Okay, or that means that whatever equation we will establish, that will only be good for a value of X, which is 0 to 0.5. Once you are analyzing your BC, okay, let's say you want to analyze a section here, you cannot use the equation that we derived in your AB, since that is only good for X, which is from 0 to 0.5. For if you are considering a section here, that is more than 0.5 from A already. Okay, so that will make it that will actually, what to call this one, that will reason out this limit that we are establishing. Okay, so VAB, if I want to, let's start with the shear. Okay, I want to get the equation of VAB, summate forces. Okay, let's say summate forces. Then you will end up here with only 20 as the vertical forces. Okay, So doing that and then bringing out your VAB, that will be equal to 20, or simply since we assume that the positive shear, if we are considering the left side as we established a while ago, is going down, then every going up, if I will just write directly VAB is equal to the equation, then every going up is positive, going down is negative. Again, or if you are confused with that, all you need to do is start with summation of forces vertical and then bring out your VAB. Okay, but if you are if you already did a lot of that and you are now what to call this one, you already mastered what will happen with VAB, then again you can follow what I am suggesting, that VAB is equal to positive going up and then negative going down. Okay, you can prove that one. So if that is the case, that the force vertical is only 20, therefore that is the equation, VAB is equal to 20. What does that mean? That is our equation, which is a constant. So that means that all throughout, okay, in any distance x from the A within your AB, so any section here within your AB, the value of the shear is 20. That is the meaning of that. Okay, it is still an equation. So let's say you want to consider x which is equal to 0.4. That is still within your 0.5 and 0. Then still x will not affect your equation. So again, that means that in any cross section here, the value of shear is 20. So at x equals 0, let's say I want to get the shear at A. X equals 0, shear is 20. And even if substituting x equals 0.5, that is at your B, that is at your point B, your shear is still 20. Okay? How about the moment? Okay? For me to get rid of your V, I will take a moment at this cross section. Okay? Take a moment here. Then, same thing, summation moment, it's up to you. Clockwise positive, counterclockwise negative, and then bring out the AB, and then you will end up. But again, if you are used in doing that, then all I need to again suggest is look at this. The unknown that we are referring to is MAB, which is a counterclockwise. That means that on the other side of the equal sign, all the clockwise, since this is a counterclockwise, the one that we are establishing, it means that on the other side of the equal sign, that is the opposite direction. So positive. So again, all the clockwise moment with respect to my cross section is positive. Okay. So what is that? What is the moment? That is only due to your 20, since that is the only force that we can see there. So 20, and then the moment with respect to this cross section is with the moment arm x. So 20 times x. That is the moment in any distance x within your AB. So that means that there is now a variable x. So at any value of x, all I need to do is substitute that x. So while the value of x will change, the value of moment will change. Okay, so that is the meaning of your equation. Therefore, there are different values of moment in any cross section within your AB. Okay, and we already established that equation, which is this. For example, you want to get the moment within x, which is 0.3 from A. All I need to do is substitute 0.3 and then solve for that moment. Okay, so that is the advantage of establishing your moment equation. Now, okay, later on we will be drawing your diagram, so we need actually to find out the shear and then moment values within the point where the load is changing. So I want to get the moment at A, substitute x equals 0, that will be 0. Moment at A is 0. Moment at B, substitute x, which is 0.5, then that will be 10. Okay, so that is the moment at B, that is moment at A. So that means that 0 at A, 10 at B. So the moment is changing from A to B. Okay, that is using your left side. Okay, that is using your left side. Now I will show you what if we will try to use your right side. This will be complicated since that is now considering more forces, but the value should be the same. Okay, the equation will be different since the distances will be different, and then the x will be different, and so with the forces will be different, but the specific value of the moment and then shear at a certain point should be the same. Okay, so let's try to focus on the right side, wherein the x will now be referred to the rightmost side, or that is your point D here. Same, I will consider now my positive here is the other way, clockwise. My positive is going up for shear. Okay, I just transfer this down, that will now be going up. counterclockwise, that will now be clockwise. And that is still correct, because once you will try to analyze, if that MAB is clockwise, then that will bend your beam going up. If that shear is going up, then your right side will be still higher. I mean, your left side is higher than your left side. Okay? So, considering your right side, focus now on the right side of the equation, or the figure, I mean. So, cut that one. I will be needing that distance x, okay, from the cut to the rightmost side. And then later on, I will be needing the distance, which is, if I were to take a moment of this force here, I need to convert this into a concentrated load, which is again 15 times the length of that, which is 2, will be 30, and that is applying on the center of your uniformly distributed load, which is 1 from B and then 1 from C. Okay. So if that is x, then what is this distance? Okay, we do not know this distance, so that will remain variable. So if that is x, but we know this to be 2, and we know that the action of that resultant is at the middle, which is half of 2 is 1 meter. Therefore, we know that this d to that middle of UDL is 3 meters. So if that is x, then that distance here, even if we do not know this distance here, will be established as x minus 3. Okay, x minus 3, that will be the distance within your section. So even if I will move that one in any point here within your AB, that will remain x minus 3. Okay, that x is following your cross section, and that x will be the same as that. So that is still constant 3. That will not move even if I will transfer this cross section here. Okay, so these are our distances. Now let's apply the same summation forces. Okay, so now your VAB is going up, so going down will be my positive. Okay, again, or you can do summation forces vertical and then bring out VAB. So since my VAB is going up, so the positive will be the going down. So what is that? Your 15 times 2 is positive, and then you're going up, which will be negative. Okay, so what does that mean? The difference, the primary difference of considering the right side and left side is your sign convention, isn't it? Your assumption of your internal forces and internal moments will be the opposite. Therefore, your assumption here, the positive assumption here, will be the opposite on the other side. So in this one, the shear, the positive shear is going up, and the positive shear is clockwise. On the other side, the positive shear is going down, and the positive moment is counterclockwise. Okay, counterclockwise, the opposite of that clockwise MAB. Okay, so that's it. If I will establish that, then negative 10 going up, and then 15 times 2 is 30. So add that one, that will be 20. So your VAB is still 20. Is still 20. It means that it is still constant within your section AB. Even I will cut at a different section within that AB, that shear is still 20, which I established on different sides of the figure. Okay, so that is a proof that it will be the same. Now let's continue on the moment. Will that be the same? Okay, so take a moment at this cross section here. Okay, what are the forces? That is the resultant of this UDL, and then of course your reaction here, which is 10. So again, I said the positive here, the positive moment will now be the counterclockwise, which is the opposite from MAB. So 10 times the distance x, which is positive since that is counterclockwise, and then the resultant of that, which is 30 or 15 times 2, it will be having a moment which is a clockwise, which will be a negative, and then the distance of that is x minus 3. So simplifying this, you can simplify that as 10x minus 30 x minus times x minus 3, or you can simplify that further. Okay, you can multiply it inside and then combine terms with x. Then that will be your equation, or you can remain this as is. But if you will try to compare that with the one we established from your AB, that is different, which is what I'm trying to emphasize a while ago. We established the equation from your different side of the equation, or different side of the figure. So you will expect different equation. But the question there, if I will substitute a value of x on the same point, even if I am using the one established on the left side and right side, that should give me the same, since I am referring to a single beam. Okay, so let's say I want to still establish the moment and then shear at your AB. By the way, since that is 20, again the same thing, even if x equals 4, okay, these distances here are established from this point D, so the x will be measured from point D. Okay, so I want to get the shear at B, so that will be 2 plus 2 is 4, so x equals 4. That will not affect this, that will 20 be 20. If that will be at A, 4 plus 0.5 is 4.5, so x is 4.5, that will not affect your 20, so it's still 20, so that is constant. Now let's go to the moment. This is what we established as equation. At x equals 4, that is your B. Substitute it here, you will end up still with 10, which is the same as that we established on the other side. Okay, that is the proof. Okay, that is the proof. Now I want to get the moment at A. Okay, get the moment at A. What is the distance? 4.5 from your reference D, since I am considering this side, right side. So substitute that here, you will end up with 0, which is the same as this, which is true because the end is a simple support. There should be no moment at that point. Okay, same thing if you will try to establish at point D. There should be no moment at point D, since that is a simple support. Okay, so that's it. We already established the equation of your moments and shear within your section AB of the beam. Okay, section AB of the beam. So once I want to get a certain value of shear and moment within your AB, all I need to do is substitute that one on my equation that I established. But of course, I showed you these two using your left side and right side. It's up to you. But I suggest, since later on we will be needing, we will be solving a lot of problem, I suggest stick to one of the side, which is your left side, since we are used in writing numbers going to the right. Okay, so let's try to copy that one. Let's try to analyze from left going to the right. Okay, but still, you can use your right side if you want. So now we only established this equation, and that is only true within your AB, which is at a distance x of 0.5 to 0 to 0.5 if you are using the left side, or from 4 to 4.5 if you are using your right side. Okay, so therefore I want now to analyze your section BC. So I need to establish another equation, since there will be additional load that is considered. So I will cut within that BC. Okay, then that will be, okay, so focus first on the left side, consider that as distance x. So summate forces vertical, again, since my positive shear is going down here, so the positive will be going up. So what is that? 20 going up. And then what else? We have here this part of the UDL, and we do not know that distance, since we said that that is x, so different distance within your BC, so let's just say that is x. Okay, I will not be considering an specific distance, since that will not be giving me an equation. If I will consider here, let's say, a specific distance, then that will only be true at that distance. Therefore, I will establish by using a variable, so that I will be changing the variable, and that will be true within that given variable. Okay, so if this is x, then what is this distance of that UDL? That is known to be 0.5, so that will be x minus 0.5. That distance is x minus 0.5. Okay, so again, go back to your shear. So going up is 20 positive, and what else? If I will try to convert this one into a concentrated load, that is 15 times the distance or the length of that, which is x minus 5. Okay, so now you have a variable in your shear equation. So you can simplify this further, or you can take it as is. So as you can see, there is an x already. So once I will change a value of x, the value of shear will be different. So that means within your BC, as we move on a different section, the values of the shear will be different because of that variable x. Okay, so now we will establish, okay, we will now be establishing the values of shear at the endpoints, or the change of load points. So at B, what will be my shear? So by the way, your equation is good only for values of x from 0.5 to 2.5, since again that is our limit from we are establishing for B to C. Okay, so if I want to get the shear at B, then what is the distance? That is exactly 0.5. So if x is 0.5, your shear at B is 20. Okay, by the way, it is not necessary that what you established here in your other section is the same on the other section on your boundary. I will explain that as we will go on the diagram. Okay, it is not necessary. It is not, actually most of the time that is different. There will be a time that is the same. There will be a time that is different at a single point on the boundary. Again, I will explain that one on the diagram. So let's just accept it as is. Okay, so again, for this scenario, this is only good for the section B to C. Okay, focus on B to C. So if that is 0.5, your VB is 20. If that is 2.5, which is your point C, 2.5 because that is 0.5 plus 2. Your BC is 2. So that is a total of 2.5. So substituting that in your X here, you will end up with a negative 10 kilonewtons. So your shear is now going up. Okay, I mean the opposite. Yes, going up. But later on, if we will try to plot that one, positive will still be on the positive of your y coordinate. Okay. So moment, let's try to take a moment, find out your MBC. Still on the left side. So clockwise is positive. Again, 20 times distance x is positive. And then 15 times the length, that will be your concentrated. So that is this one. What is the moment arm? Okay, now we need to get the moment arm. If that is the distance, then the moment arm will be half of that. Okay, if this is your distance, the moment arm will be half of that. So I think we need to simplify. This is a little bit complicated, so we need to simplify. So that will end up to 20 minus x, 20 times x minus 15 over 2 times this quantity squared. So all you need to do is change the values of x, you will end up with the moment. So I want to get at B, so x is 0.5, you will end up with moment at to be 10. Okay, moment to be 10. And then I want to establish at, okay, that should be 4.5. Okay, sorry, that should be, okay, so that is 4.5. If I will substitute that, actually that is just a typo. But if I will substitute that, that will be the same, still 20. Okay, so if x is now 4.5, which is at your C, which is recon from A, that will be 20 kNm. So let's try to establish that using the right side. I will show you. Okay, using the right side, that should be the same. So now considering this, the going down shear is positive, is the positive. Okay, so what are the shear? So this is the one going down and this is going up. So that is a negative 10. And then make this concentrated. Again, if that is x, what is this? That is 2, so x minus 2. So the shear will be transformed into a concentrated 15 times this distance. Okay, so that is going down, so positive. Okay, so this is our shear equation in your right side within your BC. So I want to get your shear at C and B. C and B. So what is the distance from your D? 2. Substitute 2. That will be negative 10, which is the same as this BC. And then at distance 4, which is your point B, your shear, substitute that there, will be 20, which is the same as your shear which we established using the left side. Okay, so the same using the right side. Now getting the moment equation. Okay, so take a moment here. Okay, so this time again counterclockwise is positive, so 10 times the distance x is positive. This will be counterclockwise, so 15 times the distance x minus 2 times the moment arm, half of that will be a negative. Simplify, you can simplify that, substitute the value of x, which is, as say, is 2, that will be giving us 20, and then at B, which is 4, giving us 10. So MB is 10, yes. MC is 20, yes. Okay, and then finally we'll end up here with the other the last segment, CD. I will cut here, the same thing happens. Okay, going up shear will be 20, is positive. Will limit here will be from 2.5 to 4.5. Okay, so that will be good only on your CD. So going up is 20, and then this is going down, so 15. Okay, this will now be a constant since we use the entire length and that is not a variable. So 15 times the entire length 2 will be 30. Okay, or simplify, this will be negative 10. So there is no x, that means that is constant from C to D. That is, shear is constant here. Okay, and as you can see, that's the same as a while ago. Your shear in your AB is constant since there is no loading within your AB. Same thing in your CD. So even if you will substitute the values, then that will not affect, okay? That will not affect since that is constant. So establish your moment. Take a moment here. Let's say that is distance x. Then we need to establish the distance from your center of 15 kilonewton meter, okay? So again, if that is x, then what is this distance? 0.5 and 1, so 1.5. So that will be x minus 1.5. So take a moment, considering your left side, clockwise is positive, okay? So clockwise is 20 times x, positive, and then 15 times 2, which is 30, times the moment arm x minus 1.5 is the negative. Simplify that one, so this is your moment for CD using the left side. Substitute your moment, your distances. 2.5 at C will give us 20 kNm. 4.5 at D will give us 0, which is again what I'm saying. Since that is a simple support, there is no moment. So I will show you using your right side. Using your right side on shear, going down is positive, so that is a negative 10, which is the same as that. All throughout, constant, so the same. Okay. Now moment, so that is the only force that I will be taking a moment, which is now a counterclockwise, which is a positive. 10 times the distance x. So 10x. Substitute. I want to get the moment at D, so 0. Moment is 0, which is the same as that. Moment at C, what is that distance from D? Is 2. So 2. Substitute, that will be 20, the same as what we established using the left side. Okay. So those are now the shear and moment equations of your example 1. Okay, so again, now we establish the shear equations of your beam. So for example, I want to know the internal moment and shear at a distance, let's say 3. So where is that? If that is 0.5 and that is 2, 3 will be somewhere here. So what equation will I be using? The equation that I established using CD. So I will be going in here. Okay, I will be going here. I will be using, it's either this. If I want to get the distance from your A, then I will be using the one, using your left side. But if I want the distance from D, then I will be using the one we established using the right side. Okay. So again, all you need to do, since again you want to know the moment and then the shear at 3 meters from A, then all you need to do is substitute 3 meters at your equation here, but that is a constant, so the same, negative 10, substitute 3 in this equation, you will end up with the moment at that distance. Okay, so that is your moment equation. I will not yet be drawing the diagram, okay. For this example, it is only for me to explain how to establish your equations. Okay, showing you that left side, considering the left side and right side, even if we have different values and different equations, will be giving us the same. Okay, even if we will end up with different equations. Now let's have another example, but this time we will try to draw now. Okay, we will just stick to one of the side. Okay, in here I just showed you that both sides are the same, will be giving us the same, but for the next example, let's just stick to considering your left side. Okay, so that we will not be having long solution. And then this time we will now try to draw the shear and moment diagram. Okay, so there are 4 segments that I need to consider: AB, BC, CD, and DE. So we will be ending up with 4 equations of shear, 1, 2, 3, 4. And then 4 equation of moment, 1, 2, 3, 4. And then using that, you can solve for the moment and shear at A, B, C, D, and E, and then we can trace that one, and that is the diagram. Okay. So let's start with solving the reaction. Take a moment at E, you will end up with reaction at that A to B, 17. Okay, you can check the algebra of this. This is just algebra. Summation moment at A will be 13, and then check that one, 17 plus 13 will be the same as this, which is 20. 30. So we are good. Now using this reaction, establish for your AB, cut. Okay, I did not show you, but imagine that I will cut it this way. Okay, we will cut it this way, just like what we did here. So cut at your AB. So the distance will be x from A. Okay, so what will be my shear? the only shear if I will cut within your AB is, the only force is 17, which is going up. So again, as I've said, considering your left side, up is positive, clockwise is positive. Okay, so let's stick to that since we are considering all the left sides. Okay, so going up positive, clockwise positive. Okay, so that will be our convention. Cut, what will be our shear? That is only 17. There will be no x there, so that is constant from A to B. Okay, so even if you will substitute at distance x0 to x1, that will still be 17. Okay, that is your shear at AB. Now establish your moment. If I will cut, that is a distance x from A, then what will be our, I will cut there, that is a distance x from A. What will be our moment? That is a clockwise, 17 times x. Substitute 0, that is your A. Moment is 0, which is true since that is a simple support. Substitute B, which is x equals 1, will be a 17. Okay, so now you have your shear and moment at A and B. Let's go to BC. Cut at BC. So your x will be within this part, and that is from A. Your x is from A to the section here. Okay, your x will be from 1 to 2 since that is distance from A. So 1 to 2. So we are limiting ourselves at BC. So that equation will be good for BC. So if I will cut here, what are the forces? Going up 17, so positive, and then going down 10, which is a negative. So 7. So again, that is constant from B to C. So V at B, V at C is still 7. Okay. For the moment, I will cut here. Your 17 is a distance x to my section here. Okay, that's a distance x. So clockwise, so that is 17 times x positive. And then your 10 here is counterclockwise. Okay, within a section here, what is the distance? Counterclockwise, but what is the distance? If this is x from A to this point, then that is 1. So what is the distance of this 10 to your section here is x minus 10. I mean x minus 1. Okay, that is this value here. Sorry, here. X minus 1. That is a negative since that will be a counterclockwise. So substitute x equals 1, that is at B, will give us 17. Substitute x equals 2, that is C, 24. Okay. Now let's go to CD. Cut here, your x will be from A still. So shear going up is 17 positive, down is 10, 5 is negative. So negative, negative will be positive 2. All throughout, your CD is a constant shear of positive 2. And then take a moment within this section, considering your left side only. Again, we will stick to the left side. So this will be clockwise positive, and the distance of that from the section here is x. And then counterclockwise 10, and the distance of that is x minus 1. And then counterclockwise 5, and the distance of that is x minus 1, 2. So the distance of this 5 from the section somewhere here is x minus 2. Okay, so this will be my equation. Substitute the values of x for me to get the C and D. So substitute at x equals 2. Your C is MC moment at C is 24. Substitute x equals 3. Your moment is 26. Okay. Now lastly, your DE, section DE, cut here. The shear will be going up 17, going down 10, 5, 15. So negative. So we'll end up with a negative. So a negative from D to E. Okay, so negative. Another typo error. I forgot to change that one. Typo error here. That should be, okay, this should be 13. Okay, this should be negative 13. That is constant. Sorry. Okay, so this is still a negative 13. Again, why? Because x will not affect that negative 13. So negative 13 at your D, negative 13 at your E. That is constant. Okay, and then moment. Take a moment somewhere here. Your distance x is from A. So that 17x is positive clockwise from section here. Your 10 is negative. And again, the distance is x minus 1. And then 5, and the distance of that is x minus 2. And then lastly 15, and the distance of that is x minus 3. Okay. So clockwise, counter, counter, counter. That's why these are the signs. And then substitute at x equals 3. X equals 3, that is your D. That will be 26. At x equals 5, substitute, that is your E, will give us 0, which is true because your E is simple support. Now we are good to draw the shear and moment diagram. Okay, so this is now your shear and moment diagram. So let's start with the shear diagram. So again, plot that one. So x and y, your horizontal is the distance. So actually drawing this is always best presented this way, this manner, wherein you have there your beams and the forces on top, and then below is the shear and moment diagram, so that if I want to consider, let's say at this point, all I need to do is consider that section. I will get the value of moment, I will get the value of shear. Okay, so this is the best way to present your shear and moment diagram. Okay, so the value of the vertical or the y is the values of shear. If you are on moment, then the y is the value of the moment. Okay, so at A, okay, these are the values that we established. Since we established that AB is a constant 17, BC is a constant 7, CD is a constant 2, and then DE is a constant 13, negative 13, then that will be constant. Okay, so at A, that is 17. At B, okay, we are still we will focus ourselves at AB. So at A is 17, at B is still 17. So that is these values. So that is the diagram. And then at we will now transfer at BC. At BC, your value at B and C is 7. So 7, 7. So all I need to do is connect. So connect that one, of course, so that you will have a shaded part. Okay. And then at CD, we established that at point C and D are 2. The same 2 and 2. So that is constant. Okay. Connect. And then lastly, at D and E is a negative 13. Negative, okay, you know how to plot. Positive on top, negative below. So negative 13 is below. So negative 13, that is the same or that is constant. So up to that is 13. So again, these are straight lines, since again that is constant. Okay. Now let's have the moment diagram. We established that one. These are the equations, by the way. We already established the value actually here. Values of moments. Okay. So at A, using this equation AB, substitute 0. That will give us 0. Substitute, what is this distance? That is 1. Substitute 1, that will be 17. To connect that one, that is a straight line, and actually later on I will discuss. Okay, if we will now go on the next unit, the reason why later on you will end up with a curved surfaces or a straight line or a flat or just like this constant. Okay, I will explain that one on the next unit. So let's just connect that one. Okay, and then using your BC equation, substitute at x equals 1, which is B, will giving us 17, so that will connect with that. And then at x equals 2 will give us 24. We solved that one a while ago. If you will go back to the previous slide. Okay, so this is BC. You have here your 17 and 24. And then next is 24, 26. And then we have here 26, 0. Okay, 17, 24, and then next is 24, 26, and then 26, 0. So that's it. Okay, the moment diagram. So how are we going to use this one? So again, if you are fond of the equation, then you will be using the equation. Let's say I want to know at the middle of the beam, which is, that is the middle, that is the entire length is 5, isn't it? So what is the middle? 2.5. So if I want to get the shear at 2.5, that is between your C and D, I will be using the equation I established at CD, which is constant. In your shear, that is constant, which is always 2. So the shear at the 2.5 is 2. And then substitute in your equation here you established at CD, your 2.5, you will end up with the value of the moment. Or, if you are using the diagram, that is the use of this diagram, all you need to do is plot that 2.5, get the equivalent shear of that, which will be giving us still 2. Okay? And then if you want to get the moment of that, okay, plot your 2.5, get that one, you will have the moment here that is between 24 and 26. Okay, you can check that one. And what you will be getting using this equation and then using your diagram should be the same. Of course, the challenge in diagram, of course, is you need to plot that one in scale, so that you will end up with the values. You can read the values in terms of the scale later on. Okay, so that is the shear end moment diagram for this example. Okay, let's have more. How about this? So I will not be discussing already here about the equations or how we'll establish the equation. Okay, it's up to you to deal with this, since again we have already this video very long. So only I will be discussing about the shear and moment diagrams. Okay, again, this is just like a while ago. Get the reactions, and then establish equations, and then using the values of x, which is actually reckoned from A, since again, as I've said, in the next examples we will just consider the left side. Okay, we will just be focusing on the left side. So again, if I will cut here, by the way, okay, so okay, I will first discuss this, since in this example we have now a moment. How will that affect our equation? Okay, so at shear, I will cut in your AB, there is no shear, since again, force, we are just summating force vertical. There is a moment, but that is not a force vertical, so that will still not be considered in your shear. So your shear AB is still 0. Okay, that is 0 within your AB. But the moment there, if I will cut within your AB, okay, I will be cutting that, and the x distance is from your point A, then you have there a moment. Then that is now be considered, since we are establishing a moment equation. So the moment should be considered. In your shear, we did not consider that 400 Newton meter moment here, since that will not be a part of the shear. Okay, since shear will only be because of the summation of forces. Okay, your moment is now summation of moments. Okay, so that's it. Now you will establish your equation for moment, since that is already a moment, not a force with a certain distance. So there will be no distance multiplied with that moment. Okay, so take a moment. Let's say I will cut somewhere there at a distance x. Then the moment there of 400 is still 400. Clockwise, that is a clockwise, so positive. So it means it is a constant from A to B. Let's proceed to your BC. Okay, BC, cut there at a distance. Then you will now have a shear, which is your reaction going up, so positive. And then your moment, I will cut here. You will have a moment of still 400, clockwise, positive, and then another clockwise, what the reaction multiplied to the distance. Okay, somewhere here is x from your A, that is a 2, so your distance of 187 to the section here will be x minus 2. Okay, establish that one, and then substitute the values, get the point B and C. These are the values. Okay, cut at CD. Finally at CD, cut that one. So what is the shear? 185 going up, 3,500 going down, so that is a constant, negative. And then the moment will be cut there, moment 400, no moment arm, since that is a moment, so positive. And then moment arm of that is x minus 2, positive, since that is clockwise. And then lastly, this is counter, so negative. But if that is at that section, 2 plus 14, so x minus 16. Okay, substitute values at C and D. We will have the moment at C and D. And then draw the shear and moment diagram. These are what we established. These are the equation. These are the values of shear. So all you need to do is plot. So we do not have shear from A to B. Okay, so leave that blank. But at B, you have a constant shear, which is 185. Positive, so that is constant all throughout CD. And then from C to D, you have now a negative. That should be a negative, by the way. I just forgot to include the negative. Where's that? At here. Okay, C to D. C to D is a negative 3312.5. That should be a negative. Okay, let's just change that one again. Typo. It's a typo error. Okay, you have now a negative. So negative. So from C to D, constant. And then now all you need to do is plot your moment diagram. So moment at AB is constant. So 400 positive, that is constant up to point B. Now at point B, from B to C, okay, your substitute the value here of 2 in your equation, you will end up with 400. I mean 4000, not 400. So still that will connect with your figure. And then substitute at x equals, okay, from A going to C is 16. Substitute 16 here. You will end up here with 6625, which we solved that one a while ago. 6625. Okay. And then finally, using your equation CD, this is your equation CD, substitute 16 from A, 16. That will give us still 6625. And then finally, substitute 18. That is your point D. Point D. Okay, so 16 plus 2 is 18. Substitute that in your equation, will definitely give us 0. Since that is a simple support, so no moment in this point. So now again, if you want to get the moment, cut that one within that section. You can use the diagram or you can use these equations. And then finally, this is fourth example. Okay, I will not. Sige, let's discuss. So we need to consider AB, BC, and CD. Why? Because in your AB there is no loading. In your BC, why is it? I will not consider B directly to D because somewhere there at your point C is a reaction or support, and this is an overhang. So I need to break this into two, BC and then CD. Okay, so this is a little bit challenging since that is a triangle, but the same thing, that is a triangular load, so all you need to do is convert that one into a concentrated. The only difference with your UDL is how to compute the concentrated value. Okay, so again, this is a simple summation moments. By the way, this one, the concentrated value of this is the area, isn't it, of a triangle. A while ago, in your UDL, in this example, where's that? In here, our values is length times width because that is a rectangular or uniformly. But in your rectangular, that is the area which is 1/2 of length times the value. Okay, so this one. So take a moment at A. So what is it will expose our unknown CV. What is the moment arm counterclockwise? Let's say counterclockwise, so that is a negative. Let's say my assumption clockwise is positive. And then how about this? The concentrated value is 1/2 times length times that height, which is 200. So 1/2 of 200 times length, which is 20, and that is acting. Okay, what is the centroid of a triangle? Is the base, 1/3 of the base from the longest side, or from the side. That is the centroid. But since I am taking the moment up to point A, so if that is 1/3, the concentration is at 1/3 to this point here, then the remaining this distance here is 2/3. Okay, that's why you have here 2/3 of that distance, 20. Okay, so that is why we have here 2/3. This is the moment arm, that is the value of the concentrated load. Same thing happens in your C. Okay, take a moment somewhere there. So now you will end up here with a reaction of going down, going up. Why is it going down? Because actually there is no loading here, so that will try to flip the beam for this point A to go up. So there should be a reaction since there should be no movement at all of going down, so that will be equilibrium. Okay, now cut here, take summation of forces. You will end up with the shear equation, which is constant. Going down is negative. And then take a moment, that is x at A, from a distance A to that section is x. So negative, that is a counterclockwise, so negative 333.33x. Same thing follows with your BC. I will cut at BC and then I will cut at CD. Okay, the challenge here is the triangular part. Again, you need to know the centroid of your simple figures. If that is a square, that is at the middle, or rectangle, that is at the middle. If that is a triangle, that is at a distance 1/3 to the base. Okay, so again, let's say I will cut somewhere here. The 1/3 will be from this point here that I established. Okay, let's say I will cut somewhere there. The 1/3 is from this point where I cut that one. The 1/3 of this concentration is 1/3 from this point here. So same thing, how to establish the equations, and then we will end up with this shear and moment diagram. These are the values we will establish. Okay, now in here, look at this. Why is it that the shear is different? This is constant, the shear and from your A to B is constant since there is no loading. Why is it that that is equation? Okay, why is it that that is equation? This is equation because now we have a loading from B to C, between B to C and then C to D. So your shear are now different at any section from within your BC and then your CD. That's why this is variable. So how to get that one? All you need to do is, again, cut at that point, get the distance from where we reckoned that one, and then substitute that as a value of x, then you will get the value. Okay, so this is now the diagram. Okay, so this is what we established. Shear at from A to B is a constant negative 333.33. And then from B to C, if you will substitute at x equals 10, you will end up there with negative 333.33. But if you will substitute 20, which is at your C, will give us a negative 8333.33 using your equation BC. Okay, but the question, why is that a curve? Okay, that will be a next discussion. That will be my next discussion on the next unit. Okay, let's just accept this one as is. But the reason why this is a curve, I will be explaining that on the next unit. Okay, now substitute x using this equation CD now, since we are on this part of CD. Substitute at x equals 20, which is your point C. That will give us a positive 1500 using this equation. Okay, what if now that is at point D? So I will substitute x equals 30, substitute there, that will give me exactly 0 shear. Okay, so now again, the reason why that is curved, I will explain that one on the next video. Now let's move on to the moment diagram. Okay, so substitute again distances, that is 0. Substitute 10, that will give us 3333.33 value here, and then substitute 10 at this equation, that will give us the same, and then substitute 20 at this equation, that will give us this value here, and then substitute 20 at this equation, that will give us the same, substitute 30 at this equation, will give us 0. So this is the moment diagram. We will try to return to this once I will discuss how to deal with this curve and then straight lines. Why is that straight? Why is that inclined? Why is that a curve? Why is that opening down? Why is that opening upwards? Okay, on the next unit. So that is how to establish the shear and moment equations and then shear and moment diagram. Okay, if you have any question, then you can comment that below the video. So thank you very much for watching.